Good afternoon, one and all present here. I, Dr. Divya Prakash, would like to invite Dr. Sanjay Dorji. Uh,
Is
he's
it
found,
live? Okay, live,
yeah,
yeah. Okay, great. Thank you.
it is live. Yeah. So now I would like to invite Dr. Sanjay Dorji, founding member of SAMA, Bhutan, and member of the advisory panel and chief weather and climate service division, National Center for Hydrology and Meteorology, Royal Government of Bhutan, for his welcome address. Now over to you, sir.
Good afternoon, Dr. Somenath Dutta, Scientist G, Regional Meteorological Center, Eastern Region of the Indian Meteorological Department, Kolkata, South Asian Meteorological Association, the partners of SABI Tribal Pune University, students and all participants, welcome to this special lecture on inertial instability and barotropic instability. Greetings to all from Bhutan. As introduced, my name is Singye Dorji. I work at the National Center for Hydrology and Meteorology. I'm also very happy to inform that more than 1,150 candidates from 50 plus countries have registered for the current lecture series on atmospheric dynamics and applications to climate sciences. The climate change, as we all know, poses a significant threat to many countries, and improving the early warning and weather and flood forecasting has become crucial adaptation measures. On this note, I would like to once again thank SAMA and the Sabi Tribal University and all the organizers for arranging this special lecture session. We would also like to acknowledge the hard work and the voluntary services of the SAMA over several years. Once again, warm welcome to Dr. Somenath Datta and all the participants joining this lecture, and looking forward to an interactive learning session. Thank you.
Thank you, sir. So, with kind permission, can I start now?
Sure, sir.
Thank
Thank you.
Now I am sharing my screen. I hope the whiteboard is visible.
Yes,
Yes.
sir. Yes, sir.
So, today we will discuss inertial instability. Inertial instability. Okay. So, to discuss the inertial instability in a simple way, first let us consider a zonal mean flow which is geostrophically balanced. That means a mean flow which is having only zonal component. And not only that, I am also telling it is a zonal mean flow, zonally geostrophic mean flow. So when I am telling geostrophic means this one, and of course it is a function of y. And this let us consider at a reference latitude, initial reference latitude, say y is equal to y naught. And then let us consider an air parcel embedded in the mean flow. Now, for analyzing the inertial instability, an air parcel embedded in a zonally geostrophic mean flow is displaced meridionally. So let us displace meridionally. It is displaced meridionally. It has reached here. And at this latitude also, we are having one mean flow. So at this latitude also, there is some mean flow is there. Suppose here it is y is equal to y naught plus delta y. So now actually we will consider the meridional equation of motion of the air parcel at the new latitude, and we will see under what condition the air parcel will continue to move away from this initial reference latitude, and under what condition it comes back. Okay, so now first let us write down the equation of motion at the new latitude. So if I write down, the equation of motion is your du dt is equal to du dt is equal to, now question one important thing, that definitely we cannot have any pressure gradient in the zonal direction. Why? It's for the mean pressure field. Why? Because had there been any pressure gradient in the zonal direction, that means east-west direction, in the mean pressure field, then it would have given the meridional component of the geostrophic wind, which is in contrary to our assumption that the mean flow is geostropically balanced, and it is having only zonal component. So therefore, equation of motion, when I will write, it will having du dt is equal to f into v, and this v is nothing but dy dt. This small u, small v, everything is related to this air parcel's motion. Okay, so air parcel's motion is like this: small u, small v, 0. No vertical motion for the simplicity. So this is, and now this equation, let me integrate it. I can integrate this equation. Let me integrate with respect to time and initial time, that means when it was here, that now when the air parcel was here, that is at y initial time, at y is equal to y0. At y is equal to y0, the air parcel was embedded with the mean flow. So therefore, all property of the air parcel happen to be same as that of the mean flow at that latitude. So that therefore, initially this was is equal to your u bar g y0 only, y0, and here we don't know. Here let me say this is equal to just ut. So, and here also if I integrate it, ui dt, so we can say at initially say y is equal to y naught, and finally it is y naught plus delta y. So therefore we get this one, that is instead of ut, it is better, let me write it is u at u, because at here at this time, what is y? Y is equal to y naught plus delta y. It is better, we can write like this. So we will get this one, u y naught plus delta y. This is equal to delta y. This we got. This is equal to ug bar y naught, then here it will be is equal to f into delta y. So let me write this equation as equation number 1. Now let us consider the second equation of motion, that is dv dt. You see we have written here small v, because we are considering the motion of the air parcel. So dv dt is equal to, here of course pressure gradient is there, minus 1 by rho del p del y, then minus f into u. This equation we are writing, this equation we are writing at this new latitude. Okay, so we get this one. Now at the same time we have also presume that our that is your zonal mean flow is geostropically balanced. So let us write that one for this latitude. So therefore what we will get, minus 1 by rho del p del y at this new latitude, then minus f into ug y naught plus delta y, this will be is equal to 0. This will be is equal to 0. So this we got. So therefore, if I just subtract this minus this, then what we will get? We will get, yeah, we will get your dv dt is equal to minus 1 by rho del p del y. This will be equal to f into so we will get this is equal to minus f into u, that u at what latitude? This is nothing but u at y naught plus delta y, then minus ug. Acha, this ug I should not write this, I should write ug bar. So ug bar into y naught plus delta y. This we got, fine. So now we have to do one thing. For this we have to use the equation number 1, that means this one, and for this we will put the Taylor series expansion. So we will get f, this we have already seen, this is equal to ug y0, ug bar y0 plus f into delta y, and here if I apply the Taylor series expansion, then we will get ug at y naught minus delta y into del ug del y, this one. So now regarding Taylor series expansion, just 1 minute time I am wasting. Actually Taylor series is a typical mathematical. Suppose one function is there fx. Suppose this function has a property is that this function is continuous. At the same time all the derivatives of the functions is continuous. Then in that case I can have an expansion like this, that fx plus h can be written as, that is your fx fx naught x naught plus h, fx naught plus h into f dash x naught plus h squared by 2 factorial 2. This is a typical mathematical concept, but very useful concept. Many places we are using. The only thing is, only requirement is that this, and it will be an infinite series. Only requirement is that this function has to be continuous and its all order derivatives should be continuous. Sometimes we call them analytical function also. And to speak frankly, our meteorological elements, all the meteorological elements, they are function of space and time, and they all satisfy this condition. So therefore we are free to use this condition. Okay, so this is the about your Taylor series expansion. Fine. So Now, so therefore now if I simplify it, then what we are getting, so this two will be cancelled. So we are getting minus f into f minus del ug bar del y. Of course, this is at where it is at y is equal to y naught into delta y. We are getting this one. So now what we'll do, dv dt is equal to this. So even from here also we can see, that that when this dv dt will be positive. If dv dt is positive, that means with time v will increase. What does it mean? That means as the time goes on, this fellow will continue moving away from this latitude. And if dv dt is negative, then this fellow will come back to here. Okay, so and when the air parcel continues to move away from the mean latitude, that is original latitude, then we will say that this is this mean flow is inertially unstable. And if the air parcel comes back, then we will say that the inertial instability, that the inertial mean flow is inertially stable. So therefore, what we get from here, that inertially unstable for inertially unstable, what you require this dv dt to be positive, and for inertial stability, we require this dv dt should be negative. Now, what does it imply? It implies dv dt positive means this quantity, this quantity, it should be negative. Entire this quantity should be negative. That means f into f minus del ug bar del y into delta y, not minus, f minus this one, it should be negative. What does it mean? If I take northern hemisphere, so we can check it actually like this: northern hemisphere, southern hemisphere. So northern hemisphere, if positive, we know. So in this case, what displacement we have given? Delta y we have given. Positive, isn't this? In this case, we have given delta y positive, isn't it? Delta y positive we gave. So if delta y is positive, then what happened? What is our conclusion? That means this quantity f minus del ug bar del y, it must be negative. What does it mean? It means that the mean flow should have a negative anticyclonic vorticity, absolute vorticity, that the mean flow should have a anticyclonic absolute. Similarly, we may check here also. Suppose f positive, sorry, here F negative, and suppose if you take delta Y positive, then in that case, what you will get? You will get F minus del UG del Y, it will be positive. And this thing, actually this thing again, it is the criteria for southern hemisphere anticyclonic vorticity, southern hemisphere anticyclonic vorticity. So therefore, what we see that what do we say, and a mean flow with anticyclonic vorticity, cyclonic vorticity is inertially unstable, inertially unstable. And stability case, you can easily check, just opposite will be the case, if opposite will be the case. Okay, so now you can interpret like this also, because we know very well that if any mean flow is having cyclonic vorticity, then in that case that mean flow is already very active. Mean flow is already very active, and for maintaining its own activity, it requires its energy. So the mean flow may have hardly any excess energy to spare for the induced perturbation. In the contrary, if we consider a mean flow which is having anticyclonic vorticity, its activity is less, and we all know very well, any air with anticyclonic vorticity, it is a source of kinetic energy. So therefore, it is having sufficient energy to spare for any perturbation introduced in it. So we can imply, we can interpret in this way also, and we can also check the energy of this inertial. For that, what we do in this equation, we multiply both sides by small v. If I do, then what you will get? We will do like this. That is v into dv dt. It is equal to minus f into f minus del ug bar del y. This big quantity I will replace by some notation, y is equal to y naught, and then you are having delta y, and I have multiplied by v. V is again equal to d dt of delta y, So therefore, if I integrate, suppose let me consider this entire quantity, let me denote it by m square, m square. So therefore, what we are getting, that is d dt of v square by 2 is equal to minus m square into d dt of delta y square by 2. This we can check it. Okay. So therefore, from here we can see that this kinetic energy of the perturbation, that means this thing will increase with time, if this is negative, and this quantity is nothing but the rotational kinetic energy of the mean flow. Is the rotational kinetic energy of the mean flow. Rotational kinetic energy. Actually, in our mechanics, when we were very small, that time we have read also r squared theta dot squared by 2. So this is your r squared delta y. This is how much deviation is there. Theta dot square means that is your angular velocity square. This one, this taking vorticity is taking care of the angular velocity divided by 2. So rotational kinetic of the midpoint. So therefore, what we have seen, that inertial instability grows, inertial instability grows at the expense of rotational kinetic energy of the mean flow. So this is about your inertial instability. Inertial instability, direct demonstration in the nature, that is whatever inertial waves we have already read, no, we have already discussed during our this atmospheric wave lecture series. So that time you remember we have discussed about the inertial waves. Actually, inertial waves generally it is found near equator. So these are to some extent example of inertial instability. So now we will go to our next topic, that is barotropic instability. Okay. Barotropic instability. Barotropic instability has a formal definition also. The formal definition is like this, that stability, that is a zonal mean flow. A zonal mean flow is said to be barotropically unstable if a small perturbation introduced in it grows spontaneously by extracting mean flow kinetic energy. By extracting the mean flow kinetic. It is a formal definition. So now how it is analyzed? So for analysis, what we do, we consider a mean zonal flow. Mean zonal flow, that means we consider a zonal flow which is having only mean zonal, which is having only zonal component, that is u bar. Of course, it is a function of y, but there is no meridional component, there is no vertical component. And of course, this is your mean flow. And of course, we consider the mean flow. Of course, we consider the mean flow is autobarotropic. Autobarotropic mean flow. Autobarotropic means already the mean flow is barotropic. We know already what is barotropic. That means there is no horizontal temperature gradient of the horizontal temperature. The atmosphere is mean flow is barotropic, and autobarotropic means if by any way this barotropic condition is disturbed, then the mean flow has its own mechanism to neutralize it. So autobarotropic condition is there. Autobarotropic condition is there. So here actually to consider the to analyze the instability, here we consider a barotropic non-divergent mean barotropic non-divergent flow. Barotropic non-divergent flow. Barotropic non-divergent zonal flow is there. Barotropic non-divergent. So for that, actually for that, we will use the what governing equation we should use for every instability analysis. Now some governing equation is required. Governing equation is the barotropic, the vorticity equation. We consider the vorticity equation. The vorticity equation is this one, that is d dt of zeta plus f, this equal to 0. So we consider a frictionless, of course frictionless is also there. I should have written frictionless. We consider a frictionless autobarotropic non-divergent zonal mean flow. So for that, the vorticity equation looks like this, ddt of zeta plus f, and this equation, on this equation we will apply the perturbation technique. This is the funda, perturbation technique. Perturbation technique we have to apply. So for perturbation technique, so for that wind you have to specify. So wind we specify like this: the perturbation has both the component y and x, both the component, this and this, both the component we are having, but no vertical. This is your perturbation quantity. This is your perturbation thing. Okay, and not only that, we also define one quantity, that is your perturbation stream function. Also we defined perturbation stream function. Also we define perturbation stream function, and so that your u prime, this will be is equal to minus del psi prime del y, and p prime is equal to del psi prime del x. Okay, and then in that case, zeta, this will be equal to Laplacian of psi prime plus your del u bar del y, because we know zeta is equal to del v del x minus del u del y. So v means this one, del v del x means you can understand this one, and del u del y, when I will do minus del, this will also come Laplace del 2 del y, and this will also come del u del y, this will also come minus del u del y. Okay, del v del x. I think I made a mistake. It's fine. Should be this one. Sorry, this one. It should be this one. So we get ultimately this one, and of course, and of course your df dt is equal to your only v into del f del y. Del f del y is nothing but your beta. Once I told also. So this is nothing but v beta into del psi prime del x. So therefore, with all this thing, what we will do, we linearize this equation. We linearize this equation using perturbation technique. And by linearization, after linearizing, what will be the form of the linearized equation? The form of the linearized equation will be this thing, that is del t of Laplacian of this one plus u bar into del x of Laplacian of this one. You will get this one, and plus beta into del psi prime del x. This is equal to 0. This is equal to 0. So ultimately, this is the linearized equation. Now, now what we will see that since you remember that I have already told in the last class that barotropic instability is its an wave instability. So here perturbation we are giving in the form of simple harmonic wave. Okay. So therefore here we will see that psi prime is equal to ay, that is amplitude is a function of y, and remaining thing is your, that is your I kx minus k, or I can write like this, not k, I into k x minus ct. This c is nothing but the phase speed of the wave perturbation. Phase speed of the wave perturbation. C is nothing but phase speed of the wave perturbation. And this ay, not necessarily it has to be a purely real number. Even if it is a purely real number, doesn't matter. I can put it as I can see it as an imaginary number also. So we will put like this. We will put like this. If I put like this, then we can see that we can find out that is what is your Laplacian of this thing. This you will get a double dot, that is second derivative of a, then minus k square into a within bracket e to the power I into k x minus ct. Achha, one thing I should tell, for wave instability, the instability condition is sought. How? Under what condition the phase speed is having a non-zero imaginary part. Let me explain. Now I have taken the perturbation like this. Okay, psi is equal to ay into e to the power I k x minus ct. Okay, now let me write this c phase speed. This is in terms of like this. That's real part of c plus I into imaginary part of c. So now if I put it here, then psi prime, this will be is equal to ay into e to the power I k x minus cr into t, then e to the power k into ci into t. Remember, this ci is a purely real number. CR is a purely real number. Ci is also purely real number. So now therefore this part has become a part of the amplitude. Even if you take this is constant, this is not varying, but this fellow varies with time. This fellow varies with time. So if this fellow varies with time, and if Ci is positive, then definitely the amplitude of the perturbation wave amplified with time. Okay. And if Ci is negative, then in that case, amplitude of the perturbation decays with time. But if I don't take Ci, if I take Ci is 0, that means the phase velocity c is a purely real number, then you cannot do any, and there is no point in analyzing because it will be always stable. I hope this is clear to everyone. to all the students. So therefore, that's why in wave instability, we seek the criteria under what condition this Ci is not equal to 0. Ci is not equal to 0. This we have to see. So now what I am telling you, see, if you do all these things, that is psi prime I have already written, this I have also calculated, and if everything is substitute in this equation, everything if you substitute in this equation, and after that if you integrate this equation, between two latitude where the flow is confined, between two latitude, then you will find, what you will find, that Ci not equal to 0 implies what? That this quantity, that between y1 to y2, this is my latitudinal belt, that is your beta minus del 2 u bar del y2 into some positive definite quantity, some positive definite quantity. I am not just writing. This is available in my lecture note, which I have already shared. Positive, otherwise I can derive here also. Some positive definite quantity dy, this is equal to 0. This is equal to 0. And we all know very well that it is a definite integral, and definite integral geometrically it represents some area. And when this definite integral has to be 0, then the some part of the area should be above the axis and some part, equal part, should be below the axis. Below the axis. That means what I mean to say, that means it must be like this type of thing. It must be like this type of thing, so that this part will be cancelled this one. So therefore this function must pass the value 0 at some, function must have the value 0 at some intermediate latitude. So that means this integrand must be equal to 0 at some latitude between y1 to y2. Now question is, this quantity is already a positive definite quantity. So therefore, a positive definite quantity into this quantity needs to be 0 at some intermediate latitude between y is equal to y1 and y2. What it requires? It requires that at that intermediate latitude, this is equal to 0. This is equal to 0. This is equal to 0. This is equal to 0 at some intermediate latitude. Let's say this is intermediate latitude. Let me say y is equal to yc. This is an intermediate latitude. This is y is equal to yc, let us take. Now, question is, what is this? This is again nothing but d dy of f minus del u bar del y at y is equal to yc. This is equal to 0. What does it mean? It means that at y is equal to yc, which is in between your y1 and y2, this quantity is nothing but the absolute vorticity of the mean flow. This is nothing but the absolute vorticity of the mean flow. That means at this latitude, this absolute vorticity of the mean flow has either a maxima or a minima. So this is the necessary condition for barotropic instability. What it says that if I consider a zonal mean flow between two latitudinal belt, say phi is equal to phi 1 to phi is equal to phi 2, or y is equal to y1 to y is equal to y2, then there must exist some intermediate latitude where the absolute vorticity of the mean flow should have either a maxima or a minima. Now, if keeping this condition in our mind, if I consider the monsoon trough, even though monsoon trough is not a complete straight line, but more or less it is east-west oriented. If I consider the monsoon trough, now we all know very well, at each and every point on the monsoon trough, the cyclonic vorticity is maximum. Am I correct, Professor Das sir? At each and every point, the cyclonic vorticity is maximum. So therefore, each and every point on the monsoon trough satisfies the criteria, necessary condition for barotropic instability. Okay, barotropic, this is true for a ridge also, because we know that at each and every point on the ridge, the anticyclonic vorticity has a maxima. So that means if I consider cyclonic vorticity as the main quantity, then I can say at each and every point on the ridge, subtropical belt of anticyclonic ridge, you can check, though at each and every point on which the what is called vorticity has a minima. So therefore, this is also this line also satisfies the necessary criteria for barotropic instability. Now, I remember when I was very small in the department, that time our very senior, very learned forecaster, they used to make one statement. I still remember. They used to say, during southwest monsoon season, the genesis of monsoon low is mainly due to barotropic instability. There may be other factor, but mainly why they are used to say, because we all know very well that the monsoon trough, eastern end of the monsoon trough dips in the head Bay of Bengal, and monsoon lows generally form over the head Bay of Bengal, and monsoon trough is a region of barotropic instability. So that's why it may be thought for the genesis of the monsoon low, initial instability may be provided as a barotropic instability by the monsoon trough, and hence we finish today. Thank you very much.
Thank you so much, sir, for this very wonderful session. So now I would like to request all panelists for switching on their camera. Please switch on your camera. Mohan sir, is it possible to you?
Yeah, I also take it.
Yeah, wait a minute. Mohan sir is.
Over, no?
Yeah, thank you. So now moving forward, now I would like to request Dr. Millie Ghosh ma'am for question answer session.
Thank you, Dr. Divya. Actually, I am seeing the box. There is no questions in the box. I'm requesting once again.
Yes. So participant, if you have any question, then please write your question and question answer box.
In YouTube also, there is no question today.
Yeah. Das sir, you are mute.
You are mute, sir. You are mute.
No, I said Dutta Saab's lecture is either so clear that nothing is to ask, or is so difficult that what to ask.
Maybe fully
Don't
confusing,
understand.
sir. Maybe fully confusing.
We used to have questions in every lecture, at least one or two questions, but so far so nobody has asked any question.
Actually, material has been shared earlier, no? Before.
Yeah. Also, you have shared the materials.
That's
tell
why.
us how-
With Mohan sir.
Good afternoon, good afternoon. Father Terasan, how are you?
Rahul sir. Oh, hello. Hello, sir.
Yeah,
How are you?
oh, great, great.
Hi, hi. Long time.
Tyagi sir.
Hello, sir. Tyagi sir. How are you?
Namaste sir.
Sir, namaste.
Tyagi sir, you are muted.
Yesterday, thank you yesterday so much.
Yeah.
So we are now coming to Chiba for JP.
Yeah.
We are
Before
having
we-
this lecture on atmospheric dynamics.
Yeah, very sir, interesting and very, I think, advanced level things.
Yes,
Yeah,
yes.
it is very helpful for the students also.
Yeah. So.
Not PhD scholar is there. I think he will be
I see.
benefited.
Okay, great.
He
Yeah, I
recently
think he has
submitted
registered.
his thesis.
He also
Yeah.
registered probably. Yes.
Yeah. So, okay, sir. Okay, sir. See you.
Yeah, thanks.
Thank you, sir. Thank you. So,
Yes, our meeting.
As is ongoing.
so now I would like to request Ashwin Jadhav for vote of thanks.
Thank you, sir. Thank you. So on behalf of organizing committee, I extend my sincere thanks to everyone who contributed to the success of 18th lecture in our weekly online lecture series on atmospheric dynamics and in application to climate sciences. We are especially grateful to Dr. Singai Dorji, Chief Weather and Climate Services Division, National Center for Hydrology and Meteorology, Royal Government of Bhutan, for his welcome address and insightful overview of this lecture series. My heartfelt thanks also goes to our distinguished speaker, Dr. Somenath Dutta, for delivering an enlightening lecture on inertial instability and barotropic instability. So I would like to acknowledge Dr. Divya Prakash for moderating the session and Dr. Milighoshni Lala for efficiently managing the question and answer segment. Additionally, I appreciate the guidance and support of all the panelists and EC members. A special thanks to all the participants and attendees who joined us from across the globe, and to the dedicated team members at Savitribai Phule Pune University for their invaluable role in organizing this lecture. Thank you all.
Thank you, Ashwin. Thank you.
Yeah. I also want to share the statistics of our today's lecture. 75 participants attended this lecture and 85% of them rated excellent and very good.
Great.
Good,
Yeah.
very good. So great. So Dutta Sahab, you have
So-
got two more lectures.
You're mute, sir.
Oh, I see.
We
Am I mute? No, I'm okay.
remember a couple of, I think 2022 and 2023. We all have seen that during most of the times of the southwest monsoon, our East UP, Bihar, they didn't receive the rainfall as such. Very less, at the end of the monsoon only they got the rainfall. So now if we remember this year's synoptic pattern, we may remember that in those 2 years, at least 2022, I clearly remember, on most of the days, southwest, that is monsoon trough was very much south of its normal position. Very much south of its normal position. So then, and we all know very well even though lot of monsoon low stores form, but whenever any monsoon lows form, monsoon lows generally they move along the monsoon trough, because monsoon trough is a, and as a result of which monsoon trough winds, but those states, mainly I mean to say Bihar and East UP, they didn't get the rainfall. The condition was very bad. And as we have seen that monsoon trough is a region of barotropic instability also. So now climate change is happening. So I think in some panel I asked this question to many many people also. So now climate change is occurring, and due to this the projected climate change, whether there will be any significant shifting of the normal position of the monsoon trough is going to take place or not. But because in that case, some region which are generally used to get good rainfall during southwest monsoon season, for example, that is what I told, East UP, then Bihar, then those states actually they will be devoid of rainfall during monsoon season, because even though there may be passage of systems and other thing actually. So from this dynamical point of view also, it can be looked that in the different scenario of the climate change, whether it has any effect on the barotropic instability, like that actually. It can be actually.
I think that the major consequence of this global warming on the climate change, and as it indicates that it is warming the atmosphere, right? So once it is warming the atmosphere, then as we have discussed earlier, there are many kinds of instabilities. Convective instability, and today you have discussed about the inertial instability, barotropic, baroclinic, and so on, so many of them. So the main consequence of the warming, as I think, is on the convective instability. All others are large scale instabilities, or the instability of the large scale flows, right? Therefore, the consequence of the climate change because of the global warming, I can see only that it will have on the on the convective instability, not any other thing. And as of now, all that thunderstorms which are occurring all over India is all because of the convective instability, grading Swiss mechanism, kicking the cloud mass upwards because of the strong heating and so on. So that's what I think. But another thing, I just today, one of our ECT member forwarded one link about some lecture series or workshop about the impact or consequence of water on the climate, not just the carbon dioxide. Everybody is talking about the increase in the greenhouse effects and carbon dioxide warming because of that. But actually, I was speaking, water vapor is one of the major greenhouse gas, right? And water vapor is the one which is responsible for the cloud formation and precipitation and everything. So probably there is a less attention towards the water, and everybody is talking about reducing the carbon, reducing the emission, etc., etc. So we need to think in a holistic way about all all those things. That's what it appears to be. It appeared to be quite interesting, that workshop which is being conducted. Again, same thing, online as well as offline. They are doing this, and of course, one of the major purposes is to earn money, because they have got hefty fee, substantial fee, about almost like $100. They are asking fee for 1 week, and we are doing everything for free for 6 months lecture series. So those things are there. But anyway, this is just a second opinion about the global warming and the climate.